It's time to start.
I think I don't need the microphone. Much? Oh, that's it. Hello everyone, welcome to the second session for physics. And I believe we have only 3 papers, except if the 4th one will be appear in the middle. And most of it is theoretical physics, but we are happy to have theoretical physics. And it's in the middle of the day, and after that it will be lunch. As all sessions, each talk will be given 15 minutes, and then afterwards, after all this session, at the end of this session, we'll have a discussion, and everyone that wants to ask a question will be please ask his questions at the end of this session. Let me open with Professor Nikolaenko from Kurchatov Institute.
From Protokinoy, actually.
Where?
It's former Serpukhov accelerator. Now it is joined to Kurchatov Institute.
Ah, okay, and from Russia. That's correct. And his work is on new measurement of CP violation phase in decay of V mesons in Atlas. You're welcome.
Thank you for possibility to present new Atlas measurement. I'll start from description of decay channel which we use. Analysis is based on run 2 data from 2015, 2016 and 17 data at 13 CV PP collisions. This result is combined with previous measurement from run 1 at 7 and 8 TV, and comparison with other experiments will be done. First of all, about data. The decay channel which we use is B sub S into J psi phi. J psi is very convenient because of pair of muons. Muons are very, very convenient object. The signal is clean, no problem. So it's oftenly used for trigger. Here, J psi signal for me plus, me minus. And decay of B sub S which we use is J psi and phi meson, phi decaying to K plus, K minus. We do not have hadron identification. However, it appeared that nevertheless, if we walk just in the near threshold for K plus, K minus pair, signal of phi is well seen, and final signal is also quite clear seen. I should mention also modification in run 2 which we did in comparison with run 1. First of all, the beam pipe became a bit more narrow, and a new detector which is called IB was installed, which improves slightly the time resolution of the detector. Also, apart from trigger for 2 mesons in JPSI, new trigger was introduced with 3 mesons. It helps with tagging. I'll recall tagging a bit further in details. And finally, we worked out a permanent control of trigger quality, which permitted us to avoid losses which we had in run 1. It was much more smooth in run 2. And the statistic in comparison with run 1 has been increased, well, actually by a factor of 4. As I said, the trigger works with mu plus mu minus. The threshold is different when physics run starts. The instantaneous velocity is very high, and threshold for accepting is higher. But when at the end of physics run, the instantaneous luminosity drops, and we work in condition when one muon transverse momentum is greater than 4, and second greater than 6 GeV. At the beginning, it is greater than 6 and greater than 11, mainly. Nevertheless, statistics is here, and we work with that. This object, B sub S, is very similar to usual K0. In the same sense, well, there are, in both cases, bottom quarks. But in this case, is second and third family, of course. This is more heavy object, but the properties like having two lifetimes, or, you know, K0 short, K0 long, observed also in B sub S. But the difference between lifetimes is, of course, much less in comparison with K0. It is of order of 15%. New phenomenon observed in B sub S decay, which was not observed here, is oscillations. If at the projection time B sub S produced with beauty quark and strange anti-quark, sometimes later situation becomes inverse, and the period of oscillation is of order of 0.3 picosecond, and the mean decay time of B sub S is of order of 1.5 picosecond. The resolution of measurement of lifetime is certainly better than 0.1 picosecond. So that is the situation. Then I should discuss how we measure CP violation phase. It is manifested in non-diagonal elements of time-dependent partial wave analysis. Since, no, first of all, theory. In standard model, the expected CP violation is attributed to so-called CP violation phase, phi s, which is connected with one of angles beta s in triangle of Kobayashi-Maskawa. I should warn people that, of course, there are several possibilities to construct triangles in Kobayashi-Maskawa scheme. In this case, one of quarks is S, and the angle is beta S. In literature, usually, or very often, they use beta other angle with triangle, not with strange quark, but just with down quark. But just a warning for readers. They should be remembered that we use just strange. That's expression, how is estimated this angle, and the CP violating phase predicted from general fit, from everything which we know about peak decays. It is estimated to this value in radians. 0.036. radian, minus 0.036 radian with very small error, of order of 10%. So it has a sample to measure this value. If the measured value is away from the theory prediction, then it means new physics. That's the objective which was used initially. Now, B sub s is spinless particle, but both decay products J psi and phi are vectors. And constructing the zero minus object from two vectors is possible in three ways, with S wave, P wave, and also angular momentum equal to 2. So there are three waves in this channel. Apart from this, we have also significant contribution not from phi, but also from K plus K minus in S wave. And it gives us another wave. So in total we have 4 waves, and we do partial wave analysis in 4 waves, time-dependent partial wave analysis. So there are explanation of angles, how they are defined in so-called transversality plane. One angle is longitudinal angle in J psi, other angle is longitudinal angle is phi decay rest frame, and the third angle is just a difference between two objects. If you look along the momentum vector between J psi and phi. So there is other complication apart from the parameter which I mentioned for amplitudes, lifetime 1, lifetime 2, CP violating phase. There are also so-called strong phases, which emerges when J psi decay to mu and phi decay to kk. So we have three decays like this. If we have information which quark or anti-quark was just at the production time, we have enough information to resolve everything. Some pictures. First of all, time distribution of our selected sample. We do not have, deliberately, we do not have cut on the lifetime. And we see a tail to negative values of time, which is produced, of course, as a result of not perfect measurement quality. But presence of this tail gives us possibility to correctly estimate our precision. We do not apply in preselection lifetime cut at all. And that is mass B sub s with background, mainly combinatorial background, but there are other components I will tell you later. About tagging. As I said, B object is produced in pairs almost exclusively. And if we look for semi-leptonic decay, not B sub s, but other beauty object in the event, and we look for semi-leptonic decays, it produces, for example, muon or electron with probability of order of 10%. And it gives us information which quark or anti-quark was in the BS at production time. There is a difficulty. Apart from this prompt decay, there is non-prompt decay where if beauty decays first to the C quark, and C quark decays semi-leptonically also, but it produces the lepton of opposite sign. But it is softer, and it gives us possibility to discriminate. Discrimination improves if we not simply use charge of muon and electron, but if we have one or several charge track in cone around the muon momentum, around momentum of third muon or around momentum of electron, it improves the situation and gives better tagging power. So what is shown here is, first of all, there are cases without supplementary tracks. You see that the probability to have correct identification is of order of 0.7, and other possibilities of order of 0.3, like this. And on the right, that's momentum charge of all tracks in cone, weight proportionally to the track momentum. And this is a calibration curve which we obtained from the data, exclusively from the data. Okay. We rest very quickly. Fit model, as I said, we work with assuming signal as Gaussian with time resolution estimated from the data. Again, about tagging. If we do not have tagging, non-diagonal terms which give us information about phi s originate via cosine of this angle, but angle is small and it doesn't give precision. If we have tagging, we have information from sine phi, and it improves very significantly the precision which we have. That's a table. Left part is time part, right side is angular description of waves. 4 diagonal and 6 non-diagonal. Background mainly combinatorial, but there is also some contribution, 4% from non-strange beauty and 2% from lambda b decay, because of we do not have hadron identification. There are angle distributions, as I mentioned, 3 angles. On the top that's a sum, below that's a background distribution for this angle, and this is for our signal. And on the bottom, comparison between the data and fit expressed in just in errors. Systematic uncertainties are here. That's a good, more than a half work was spent just for this, but I don't have time to describe. Comparison between run 1, run 2, and combined result. Combination was done with a so-called blue package, best linear likelihood estimate in root. There are parameters which I mentioned, our measurements, combined already. Phi s, difference in inverse times, mean inverse, mean lifetime inverse, 3 amplitude squared, so-called angles, supplementary, so-called strong angles. Comparison with other experiments.
Go to the conclusion, please.
Conclusion is here. That's a conclusion.
Okay.
That's our result. That's the last CMS result. That's CMS from run 1. That's LHCb. You can see values. We have phi s minus 0.076 with error 0.034 statistical and 19 systematical. Statistical error dominates. It gives us possibility for further improvement. A similar measurement in LHCb was published. They included only 15 and 16 data, and you see that for phi s value is very close. In previous picture, what I'm showing, this is not simply our channel with J psi phi, but that's LHCb took average with 5 other channels. They are experimentally designed specially for this work, difficult to compete. But In our channel, the result is very, very, very close. And finally, if somebody interested, I presented references. This paper is just at the output tray for improvement.